It is a pleasure to welcome you to the fourth edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The Pan IIT Lecture Series on geotechnical engineering is consisting of 6 talks, which have been delivered by the pioneers in the field of geotechnical engineering from different IITs. The following lecture is the second talk of the session 2 of the lecture series. This lecture is on support system for tunnels constructed in squeezing ground, which will be delivered by Dr. Ketan Arora. Dr. Ketan Arora is currently working as an assistant professor in the Department of Civil Engineering at the Indian Institute of Technology Roorkee. Dr. Arora has completed his PhD in Civil and Environmental Engineering, Geotechnical, from the Colorado School of Mines, USA. He also holds M.Tech in Rock Engineering and Underground Structures from IIT Delhi and B.Tech in Civil Engineering from Sardar Vallabhbhai National Institute of Technology Surat, India. Dr. Arora has both academic and industrial experience in the field of geomechanics. He has also served as a postdoctoral fellow and an adjunct faculty at the Colorado School of Mines, and tunnel engineer for a consultancy firm Aldia Services Incorporated, USA. Dr. Arora's research interests lie in the domain of design and analysis of underground excavations, rock mechanics, and rock engineering, and geomechanics for energy and mineral resources, instrumentation and monitoring of geotechnical structures, environmental impact assessment of civil and mining activities, etc.
Thanks everyone joining us from the different part of the world. I'm Ketan Arora, currently working as an assistant professor, and thank you Satyam for a nice introduction. And the topic of today's lecture is support system for tunnels constructed in squeezing ground. So this will be the flow of the lecture. First, I'll give you a brief introduction to what is squeezing in tunnels, and then we'll move to what is preliminary analysis that we had done back in like 2018. Then we'll discuss like few case studies. Then finally we'll move to the quantitative analysis, which actually involves a nice experimental setup, a physical model test setup. And then finally we'll provide the support recommendation, and finally we'll conclude this lecture. So what is squeezing in tunnel? As you can see in this tunnel cross section, there's a tunnel of radius r excavated in isotropic stress field P0. Isotropic stress field P0, and as Professor Gaurav Tiwari already explained, that there is an onset of like plastic zone upon excavation because of the yielding of the rock or soil around the tunnel boundary, and then there is an elastic zone. So we'll say that this tunnel is in a squeezing ground condition when this convergence U of the tunnel increases with time even after the excavation is complete. And the primary reason for the squeezing is high plastic deformation of the yielding of the rock or soil around the tunnel boundary. But since this is a time-dependent deformation, so squeezing is often related with the physical processes such as consolidation, creep, and it is different from like chemical swelling, because in this case we have like negligible volumetric deformation, whereas in case of swelling we have high volumetric deformation and it is a chemical process, whereas squeezing is a physical process. So just to give you an idea like how much amount of deformation can occur in squeezing ground conditions. So this picture is actually from a Lion Turin base tunnel. We have like 2 cross sections. One is like this one. Laser pointer. So first is like this one, and second is like this one. So in this cross section, they had a competent rock mass, which did so show like significant amount of squeezing, and then all of a sudden they were excavating in a shear zone, and in shear zone they had a weak mudstone. So just to give you an idea about the weakness, how to quantify that weakness, weakness can be quantified in terms of like the competency ratio FC, which is the ratio of the compressive strength of the rock mass to the vertical stress, or it can be like principal stress as well. So this FC was 0.12, and from the literature it is like quite clear, if FC is less than 0.5, then you are excavating in a squeezing ground condition. So the primary reasons that were identified for this large time-dependent deformation were presence of the clay mineral, incompetent rock mass, and high ductile behavior of the ground. That means the ground is maintaining its continuity. So this figure just shows the timeline of all the methodologies that have been proposed till date to study like tunnels in squeezing ground condition. And in each of these approaches, there have been like different definitions of the squeezing that have been proposed over the years. and different definitions are actually based on the stress level that you are experiencing, the different conversions that you can have, the different tangential strain, the condition of the rock mass, mineralogy. So they're like different definition of the squeezing. But based on the ISRM suggested methods, the definition of the squeezing is like you have like large time dependent deformation in a clay rich rock ground at a very high NCQ stress. So over the years, all the approaches that have been proposed, they can be broadly classified based on the ground material in which squeezing is associated with a clay rich rock or soil. It has been also associated with the rock mass quality Q system, in which they have a correlation. If Q is less than a certain value, then your tunnel will be in a squeezing ground condition. And then you have like factors like FC competency ratio, which I've already explained in the previous slides. And then the other classification can be based on like critical stresses and strain, which I've already discussed. Let's say the stress level is, let's say if you have an overburden greater than like 500 meters, and then your tunnel is in a squeezing ground condition and ground maintains its continuity. If tangential strain, these are just an example. So that's how the squeezing was actually studied in the past. Then we have like models based on the material flow properties, for which we have a viscoelastic and viscoplastic model, and then we have like other criteria which are based on like the field observations and empirical correlation. But the major limitation of all those criteria are they're like either site specific, they hold discrepancies between each other, highly empirical in nature, and derived from the limited field and laboratory experimental data. So in this lecture, I'll be talking about like two approaches. First one is like preliminary estimate, and the second one is like quantitative estimate. In preliminary estimate, we are saying that the squeezing is solely associated with the yielding of the material. We are not discussing any model, we are not discussing any creep consolidation of the material. We are saying that the material has yielded. And the critical parameters are overburden, strength, and elastic properties of the material. Whereas in case of like quantitative analysis, we are actually studying the creep and consolidation of the properties of the material. And for that, we have a viscoelastic or viscoplastic model. So first, we'll start with the preliminary estimate. So this study was done back in like 2018. And in this study, what exactly we did, we combined like a few of the existing theories of like tunnel excavated in like clay rich rock. First one was given by Terzaghi, in which he associated squeezing mainly with the presence of like clay mineral in the rock. And then the second theory was proposed by Beck in 1969, where he proposed a stability number N, which is the ratio of the sigma V to undrained shear strength of the rock mass. Sigma V is a total vertical stress. So this was a total stress analysis. And if this value of N is greater than 7, then we'll have like high amount of squeezing. And as N increases, the amount of like deformation within the tunnel or U conversion that we have studied will increase. Okay. Using this N, and sand shape model, which is like stress history and normalized soil engineering property model by proposed by Ladd and Foote in 1969, Gutierrez and Zia in 2009 proposed a study like proposed a study like a study for the yielding of the clay material around the tunnel boundary. If and they calculated a critical stress. If that critical stress is greater than any of the major principal stress at the tunnel location, then it is in a squeezing ground condition. But our focus was on clay rich rock, and we need to determine the equivalent parameters equivalent to like undrained shear strength of the soil, equivalent parameter for a rock mass. So for that, we used a correlation, we used an experimental correlation in which we actually studied the UCS of the rock mass with the stress at which like the yielding was observed. So these two equation 4 and 5 will provide sigma y prime, which is like equivalent to the SU, the stress at which the yielding can be observed in the rock mass. And finally, we combine this equation and propose the equation to calculate the critical stress at which squeezing can be observed. So if major principal stress, effective major principal stress at the tunnel location is greater than sigma critical calculated by equation 6, then we say that the tunnel is in a squeezing ground condition. But again, the squeezing is not quantified. So for that, what we did, we proposed a squeezing number S, which is actually the ratio of the sigma prime to sigma critical. Sigma prime is the effective major principal stress at the tunnel location, and sigma critical as calculated by the study. So further, we wanted to further explore into it, like what does S represent. So for that, we carried out like case study of like 4 different tunnels that have experienced squeezing in the past. So the first one was John Street Pumping Station Tunnel in Canada, then Laodongxin Tunnel in China, then Ulubud Project Tunnel in Turkey, and then Stillwater Tunnel in United States. So these are the rock mass properties of like 4 different tunnels. These properties have been taken from different studies. You can clearly see that the GSI, geological strength index value of the rock mass is like in case of like Stillwater tunnel only, it is like crossing 55 for a squeezing ground condition. It is close to 55, otherwise it's like very low. It's a very poor rock mass. It's basically between class 3 to class 3, class 4 rock mass, or in some cases it is also like class 2 rock mass. So first about John String Pumping Station Tunnel. So originally the tunnel was built in like 1925, but in 1980s they proposed extension of like 1.5 diameter tunnel to carry the water. So the tunnel is located on a land reclaimed from Lake Ontario, and the geology of that area is like it contains of like thick sequence of like thinly bedded or laminated shales. And in between we also had like calcareous mudstone, siltstone, and occasionally sandstone with interbeds of siliceous or argillaceous limestone. So basically we had a clay rich rock, or we can say shale or mudstone at that location, and then we selected like a few critical cross section, but this tunnel was excavated at an overburden of like 15 meters to 30 meters. But the major issue was that the horizontal stress at that location was 13 to 30 times of the vertical stress. So that was a primary reason for the squeezing. So the graph on the left shows like the ground profile, and with respect to the tunnel axis, you can clearly see in this case, at this location, there is an overburden of around 25 meters, and the maximum overburden was around 30 meters. But because of the high horizontal stress, we had a squeezing at that location. So for the 17 critical cross sections of that tunnel, we calculated the sigma critical as proposed in our methodology at 17 critical cross sections. And then we also observed the major principal stress, and then we critically observed the sections at which the S was actually greater than 1, and then we compared with the field observations. So you can clearly see the comparison of the critical effective stress for squeezing and the effective horizontal stress at the tunnel location. In this case, we are using effective horizontal stress instead of effective vertical stress, because horizontal stress is actually the major principal stress. Next was Laodongsheng tunnel in China, and this tunnel actually experienced like massive amount of squeezing in the early stage of construction. Even they installed the steel ribs on site, and they even failed like after a few days of installation. So this tunnel was around 7.5 kilometers long and was excavated at a maximum overburden of like 370 meters, and the rock mass was ranging from like type 3 to type 5, and mostly squeezing was observed like in a rock mass of type 4 and type 5. So again, the rock mass was a mudstone rock mass, and it was like very incompetent, and the uses of the rock mass was ranging from 1 megapascal to 13 megapascal. If you can recall, like the competency ratio parameter, which was a ratio of like sigma cm to sigma v. So in this case, we have overburden of 370 meters, and the UCS is between 1 to 30 meters. Even if we assume the average value, which is roughly around 6, 7, even in that case, the FC is less than 0.5. So squeezing was expected in terms of like the competency ratio. But again, like we did a similar analysis as in case of like the first project. So we selected like few critical cross sections at which like squeezing was observed, and the mudstone was present, because this tunnel was excavated in mudstone as well as through the sandstone as well, as you can see uh, in this plot. The third project was like Uluwabad project tunnel in Turkey. So again, we did a similar kind of analysis. Again, in this case, we also had a clay stone, which is again another like clay rich rock, and we did a similar kind of analysis. But in this case, all the points that we had selected, all of them had actually experienced a squeezing, and our model was also predicting that. But the value of the squeezing number S was different, which we are going to discuss in the coming slides. The third one was like Stillwater Tunnel in United States. So it was a 13-kilometer long tunnel in the state of Utah in United States. Again, this tunnel was also excavated in like clay rich rock, and this also experienced like a squeezing. But in this case, in the literature, we had like instances of like light squeezing and moderate squeezing reported for like at different cross sections. So this was a similar kind of analysis, but finally what we did, we compared the squeezing number S for obtained from all the 4 different tunnels, which are shown like in this figure, and then we compared with the in-situ observation. For example, for John Street Pumping Station Tunnel, the parameter squeezing number S was varying from like 0.26 to 2.97. Just to recall, if S is less than 1, we have like no squeezing. But on site, it was observed that there is a moderate time-dependent deformation of the tunnel. In case of loud junction tunnel, the squeezing number was as high as like 7.78, and there was a settlement of about like 400 mm uh, at the crown, and the 275 mm at the crown, sorry, and 402 mm at the horizontal level. In Ulawad project tunnel, the S was like around 22, and in that case, we had a tunnel closure, or like the ratio of like convergence to the radius of the tunnel was around 14%. In Stillwater tunnel, the S was like comparable to the loud junction tunnel, around 7.55, and we had a moderate squeezing in class 4 shape. So what we did, we combined our study with a study by Hook and Marinos and proposed this table. If S is less than 1, then we have like light to no squeezing, and we'll have like very few support problems. Likewise, if as S increases, the amount of like the tangential strain in the tunnel will increase, and so the support requirement will increase, and then we can have like unanticipated like support issues. So this criteria actually provides a preliminary estimation of the tunnel alignment, and this is currently in practice. That means it has been adopted by the industry whenever they are excavating in like clay-rich rock, and be it like excavating in like sticky clay or excavating in like mudstone or shale. They are actually using this criteria to have a preliminary estimate of the amount of squeezing that a tunnel can experience. Next, about the quantitative analysis. For that, we developed a physical model test setup. So this physical model test setup was developed like during my PhD at Colorado School of Mines. So this physical model test setup had like three major components. So first one was this true triaxial cell, marked as like number 7. So this true triaxial cell can actually accommodate a cubical rock specimen of 30 centimeter, and can independently apply the stresses up to like 13 megapascal independently in all the three directions. So for a mudstone, if we assume the average unit weight, then that is approximately like 500 meters of depth. So it is actually simulating the 500 meters of overburden. And the rock material that we tested and the setup had a UCS of 4.5 megapascal. So we were actually able to simulate the competency ratio of about uh, like of roughly around like 1/8. So this animation actually shows like while the cubical rock specimen is loaded in a true traction stress state, this miniature tunnel boring machine was excavating a cavity. So just to recall, the dimension of this cubical rock specimen are like 30 by 30 by 30, and the diameter of this tunnel was like 5 centimeter. And the third important component beside like true traction cell and the miniature tunnel boring machine were the instrumentation and monitoring system. So in this case, we had like two kinds of instrumentation. First was to measure the deformation around the tunnel boundary. Second one was to measure the deformation at the tunnel boundary. We wanted to monitor the damages as well using acoustic emission sensor installed on the surface of this cubical rock specimen, but unfortunately the inclination was very high in a weak material like mudstone, so we were not able to do that. So for that, actually, we use a specially prepared a synthetic mudstone. So the motivation was came from like a preparation of like a synthetic Melbourne mudstone in the laboratory that was named as like Johnstone back in like 1989. So we followed the similar process. We mixed a small amount of cement in a pulverized mudstone, and then we prepared a synthetic mudstone in the laboratory, and then we did a characterization, and then we obtained like a cohesion and friction angle using the traction test, using the unconfined compression test, and then we also obtained the creep parameters, and then we fitted those creep characteristics in the Burgers model, and then we obtained the Burgers model parameter. So what we found that this synthetic mudstone had similitude with the naturally occurring mudstone in terms of like the engineering behavior, and it was showing like significant amount of creep, or simply we can say that squeezing characteristics. Then what we did, we prepared a cubical specimen of this kind of rock, and then we tested in a physical model test setup. Which had a true triaxial cell, miniature tunnel boring machine, and instrumentation and monitoring. So over here we did like three kinds of tests. So the first one was preliminary test to check the capability of the test setup to simulate tunnels in squeezy ground. Second one was similar test, but in case of like isotropic stress condition, but on unsupported tunnel. The third type of test was on supported tunnel, and the stress level were like similar to the test number two. So I'll directly discuss the test on the unsupported tunnel. I'm not going to discuss the preliminary test. Okay, so in this test, what we did, we applied a isotropic stress P naught on the cubical rock specimen, and then we drilled a tunnel of diameter 5 centimeter and 160 long, and then we increased the P naught in stages. You can see over here the ratio, how ratio of like P naught over sigma c was increased in stages, and the time of loading for each stage was based on the onset of the steady state. Now, what is steady state? In terms of creep, when the strains are like linearly increasing with time, that means we have hit the secondary stage of the creep, then that is known as like steady state. So whenever we observe the secondary creep, we move to the next loading stage. And we monitored the damages at the tunnel boundary using this borehole caliper, which actually provides a change in diameter of the tunnel with distance from the tunnel face. So this is tunnel face. So this borehole caliper was moving like this. It had a robotic arm. So with time, it was monitoring the change in diameter at different location. Let's say we were taking readings at an interval of like 30 centimeter, and the deformation around the tunnel boundary were monitored using embedded MPPEX. So these MPPX, since they were glued on a Teflon strip, these strain gauges were glued on a Teflon strip instead of directly attaching it to the surface of the rock. So that's why this kind of analysis was only qualitative in nature, but not quantitative, because it was not providing the absolute value of the strain. It was just providing the trend of increasing strain around the tunnel boundary. So the major outcome from this kind of test was we had a longitudinal displacement profile. So longitudinal displacement profile, or LDP, provides a change in the tunnel strain. In this case, the tunnel strain is like U over R with distance from the face. So as you can see in this figure, so this is the longitudinal profile of the tunnel, and this is the tunnel face. So it provides a change in the tunnel strain with distance from the tunnel face. So as you can see that with time in each loading stage, the longitudinal displacement profile is shifting upwards. Now, what is the role of like longitudinal displacement profile? So it is like one of the most important element of the convergence confinement method, which Professor Tiwari had discussed in the previous lecture. So this is like one of the most important, and now it is a time variable in squeezing ground conditions, so that will make the convergence confinement method very complex. But if we have the equation, then we can predict the ultimate deformation that the tunnel can experience, and how much we have to over excavate, or how much the stiffness of the support has to be increased. So for this unsupported tunnel, this graph actually provides you the variation of the tunnel strain U over R with time at any tunnel cross section. So the best fitting equation was Q over R is equal to A minus B times D to the power T. So this provides the increase in tunnel strain with time, where T is a time dependent parameter, and it was found to be constant independent of everything, and it was like 0.98. Parameter A represents the ultimate strain of the tunnel. If you apply the boundary condition, like if time tends to infinity, then U over R will be equal to A. And at time t is equal to 0, U over R is equal to A minus B. Further, the parameter A was found to be the function of capital X, which is actually normalized distance from the tunnel face, as we have observed in case of like longitudinal displacement profile. And then it was also a function of P naught by sigma c, which is like basically inverse of that competency ratio in this case. Whereas the parameter B was found to be the function of only P naught by sigma c, and this was solely based on the experimental observations. The third type of test actually that we did was with a supported tunnel. So test was similar to the case one. The only difference in this case was that we had a support element, which was actually ASTM 6061 thin aluminum cylinder with a radial strain gauges installed onto it, with distance from the face, and these strain gauges with a that borehole caliper were providing the deformation at the inner face and outer face of the support system. And similarly, we had a longitudinal support displacement profile in this case. And in this case as well, the support displacement profile was found to be shifting upwards, but the increase in strain was not very significant. And this kind of support system was actually very stiff and that what is stiff support and what is the parameter used to define like the stiffness of the support, that we'll discuss in the coming slides. So likewise, the tunnel deformation can be defined by this equation at any cross section, as minus bs times d to the power t. So ds was again like 0.98 constant, whereas like bs and as are again like if we apply the similar boundary condition, but a subscript s actually represents parameter a with for a supported tunnel, whereas a represents for unsupported tunnel. So as was found to increase with the increase in x, which is like normalized distance from the face, and p naught, which is like applied isotropic stress, or like you can say it depends on the loading stage in for this experiment. But it was found to decrease with pi, that means whatever internal pressure that the support is providing. PS was found to increase with P naught, similar to like unsupported tunnel, but it decreases with PI. So we combined the observation of the two experiment, and then we calculated what is a percentage reduction in the tunnel strain because of the support installation. And when we compared the two experiments for each of the loading stage, we observed that the support system was reducing the tunnel strain by approximately like 96% for each of the loading stage. If you come, if that you can easily get by comparing all the longitudinal displacement profile at the same loading stage, because in case of loading stage we had a variable p naught by sigma c, so you can compare that for each of the loading stages. So we had a 96%. So finally what we did, so from this analysis we had this 6061 thin aluminum cylinder as per the ASTM standards, so had a certain characteristics which with respect to the stiffness of the ground, and that characteristic in 1981 were proposed by Einstein and Schwartz in terms of the compressibility ratio C star. So what is compressibility ratio? It is expressed by this equation, but basically it provides the stiffness of the ground or geomaterial or material around the tunnel boundary, rock or soil, with respect to the stiffness of the support. That means if the compressibility ratio is 0, that the support is like very stiff. If the compressibility ratio is like infinity, that represents like no support condition. So what we did, we compared like our analysis result, that means what was a reduction in the convergence because of the support installation, with the observations of like at the Laodongsheng tunnel in railway tunnel which was constructed in China, which we had discussed earlier in the preliminary analysis. And we had like 4 data points for the support compressibility ratio for that, and then we also had like the reduction in the tunnel strain because of the installation of that particular type of support. We also did like another type of test. We varied the liner, and in that case we had a PVC liner instead of like a 6061 thin aluminum cylinder. We compared the observation with the still water tunnel as well, and then we also had a data point from the present study. So from this present study, the compressibility ratio was close to like was very close to like 0. That means the support system was like very stiff. Whereas in case of like Laodongsheng tunnel, the compressibility ratio was around 20 to 23. That means the support was not very stiff and it's a flexible support system. Just to give you an idea, if the support system is like very flexible, then it won't hold its shape, and then you can have a zone of like stress concentration within the support system, and that can also cause a local failure within the support element. So finally, we propose this equation. Let's say if we have to reduce, let's say, unsupported tunnel and squeezing ground condition is experiencing like tunnel strain of like 25%, and if you want to bring that those 25% down to let's say 2% or 1%, then with this we can calculate what is a reduction in what is a percentage reduction in like delta u over r, and based on that we can select we can come up with a support compressibility ratio using this equation, and based on that we can design the thickness of the support system for a given material. Okay, so just to conclude the study, so in this so first task we had like few tasks. So the first task was like review and case study, and from that the major outcome was we had a parameter s, which was also known as like squeezing number. So that can provide a preliminary estimate of the amount of the squeezing that any tunnel or any underground construction project can experience. Then we proposed a novel physical model test setup that can actually simulate the tunnel excavation in squeezing ground condition or tunnel excavation at a very high in situ stress. And this setup can be used for like other applications as well. Then we proposed preparation of a synthetic mudstone, which is like very repeatable in nature because we were using all the standard materials. So this kind of material can be replicated in any laboratory in any given condition. The only condition was if we just maintain the temperature and humidity. Then we carried out the physical model test for a supported and unsupported tunnel. So we had like convergence with time and squeezing ground for a supported as well as unsupported tunnel. And based on the analysis and synthesis of the test results, we had an equation of the longitudinal displacement profile, which was like U over R is equal to A minus B times D to the power T. So with that equation of the longitudinal displacement profile, we can incorporate that in the convergence confinement method. And that actually provides us a rational approach for the design and analysis of the tunnels and squeezing ground condition. And whatever criteria we had is actually experimentally verified. So if you want to know more, these are the publications from this work. Even though in this presentation, I have limited myself to the selection of like the support system, but we did like some more work on squeezing from like calculation of the conversion of the tunnel. We discussed a theoretical model. We have also discussed like how this physical model, the setup was prepared. So I have listed all the publications. If you are further interested in reading more on this research, then you can refer to these publications. And for this research, actually, I would like to thank my PhD advisors and the sponsors of the research, UTI at Colorado School of Mines, US Department of Transportation for funding our UTI Center at Colorado School of Mines. And I would like to thank AGERP organizing team for giving me an opportunity to discuss my research. And I would also like to thank my current employer, IIT Kharagpur, for giving me a platform. Just to give you an idea what exactly we are doing at IIT Kharagpur. So I am associated with the Department of Mining Engineering, and at Department of Mining Engineering, we had actually one of the largest group in rock mechanics. And these are the area of the research on which we are working, from elementary rock mechanics to design of underground excavation to blasting, ground stability, design of like support systems. So we have like a group of around 7 faculty who are actually working on like these problems. And like IIT Kanpur, we are also open to collaboration. We would also be happy if you can visit our campus. We have like excellent state of the art like facility for rock mechanics testing, as well as we have like dynamic testing of rocks. We have like blasting facility, and we have like many field monitoring tools. We have a very nice computational geomechanics laboratory as well. And with this, I would like to thank everyone for their time, and I would be happy to answer the questions. Exactly, these advances can actually be extended. And when I was working as a tunnel consultant in US, so that time actually we implemented this to like one of the project in Texas. So we have used like squeezing number S. We calculated squeezing number S for the alignment of the tunnel, but we have not tested the other criteria yet on the field. But hopefully somebody can do that in the field. Thank you. Thank you for your question.